All right, good morning. We're very excited to have Corinthia Aberlé here, who is a second-time Topos RA, the first ever one.
I don't think that's true.
Oh no,
Harrison.
Did Harrison come twice? I guess I have to restart.
Don't
Did
snub
Harrison come
Harrison.
twice? I wasn't here yet.
No, keep this in.
We'll cut it in post. Corinthia, the second-time Topos RA, I have just learned, who's working with me and Evan on formalizing a bunch of great stuff in category theory and double category theory, also talking to Dana Scott a fair bit. Corinthia studied at Oxford, is now at CMU with Steve Audi and Frank Fenig, and we are very excited to hear what she's been doing. Corinthia.
Thank you. Yeah, and really nice to be back giving this seminar for, as mentioned, the second time. But so today I'm going to be talking about something pretty near and dear to my heart, which is synthetic mathematics, logical frameworks, and categorical algebra. And if you were here for my talk last time, this last part might sound a bit familiar to you. But so I'm going to talk about how some of these new things that I didn't talk as much about last time kind of link up with that. And as Kevin mentioned, some of the ongoing work I'm doing this summer. So let's get started. So, like I said, these are topics near and dear to my heart: synthetic mathematics, interactive theorem proving, and categorical algebra. And if you don't know what any of those are yet, don't worry, that's kind of going to be the main point of the talk, is to kind of get clear about what those are and how they kind of link up. And in particular, how we can sort of use all three of them in tandem to do some cool stuff with category theory and type theory and all that kind of stuff. So, and I'm aiming to have this talk follow kind of a sort of dialectical process, which it's going to be sort of mostly driven by questions. So, first question: what is synthetic mathematics, and why should I care? Second question: what is a logical framework, and how can I use one to help me do math? Third: what is categorical algebra, and what are its limits? And yes, that is a pun. What do synthetic mathematics, logical frameworks, and categorical algebra have to do with each other? So let's get started. So first question: what is synthetic mathematics? And I'm going to just quote everyone's favorite categorical encyclopedia, the NLab, which says it, I think, decently. So in synthetic approaches to the formulation of theories in mathematics, the emphasis is on axioms that directly capture the core aspects of the intended structures, in contrast to more traditional analytic approaches, where axioms are used to encode some basic substrate out of which everything else is then built analytically. So the typical example here is that if we're working in sort of standard set theoretic foundations of classical mathematics, everything's built out of sets, at least in principle. That's the analytic approach, whereas the synthetic approach might say, okay, if we're interested in studying something like some particular class of topological spaces or some other kind of more interesting mathematical structures, let's just directly axiomatize what are the key properties of those. And so the sort of classic example that I like to introduce this sort of bifurcation between analytic and synthetic methods is geometry. And so the sort of example of a synthetic theory is Euclidean geometry, where you have points, and normally in normal Euclidean geometry you have lines, and then you define line segments. But in this case, I'm going to be taking line segments as primitive just because A, they're easier to draw, and B, it's going to link up more nicely with some stuff later in the talk. But the important fact is that these notions of point and line segment are just primitive, unanalyzed. We're not saying points or lines are made out of something. We're just saying stuff like, for any two distinct points, there is a unique line segment connecting them, and that's all we say about it. And then we can use that to build up more complicated definitions, like a triangle. A triangle is a figure formed by three line segments connecting 3 points, like so. And so contrast this with, for instance, Cartesian plane geometry, which is maybe certainly the more standard modern approach ever since Descartes. But so the idea here is that we define points as pairs of real numbers, and then we can actually define e.g. line segments as being sets of points, i.e. sets of pairs of real numbers defined by some linear equation and some inequalities. And then, importantly, this approach doesn't have any additional axioms. It just assumes whatever the axioms are of the ambient set theory or whatever it is you're working in, and then just builds everything up from there. And so then, again, we can define more complicated things like triangles and stuff like that. But now they're, again, built up out of these like sets of points that we built from this more basic structure. And so then here's a question. Why be synthetic? Like, so isn't the reason we use Cartesian geometry over Euclidean geometry these days the fact that it is just strictly superior? Like, we can actually do a bunch of nice equational or inequational reasoning to talk about how lines intersect and areas and volumes and all that kind of stuff. Why would we want to leave the notion of, for instance, points and line segments unanalyzed when real numbers seem so much more powerful? Well, so what I want to first point out is if you follow this same line of thinking through, then, okay, really, you should also analyze your notion of real number. And then if you, again, follow the standard approach, that's going to give some analysis of real numbers in terms of sets. Maybe it's Dedekind cuts, maybe it's Cauchy sequences, something like that, if you've ever come across those sorts of definitions. And so then now we've got everything defined in terms of sets. And then what are sets defined in terms of? Yeah. But the point is, we do have to stop somewhere. And the idea of synthetic mathematics, the sort of like fundamental idea, is that we can actually do some interesting things by choosing very carefully where we choose to stop. And so here's something I want to point out. So no one in their right mind actually uses these standard set theoretic constructions of real numbers directly if you're doing like geometry. Like, you are not doing geometry by like looking at like, okay, I have this Dedekind cut and this other Dedekind cut and then a bunch of other Dedekind cuts in between them. No, you're using some kind of axiomatic formulation of the real numbers, and then you're just appealing to the fact that we have these synthetic, the set theoretic construction as essentially like a guarantee of consistency for those. That's what I just said there. And so when you think of it this way, I kind of like to think of this with kind of a sort of computer science analogy, which is that a synthetic definition of a mathematical concept is basically an interface to that mathematical concept. It gives you axioms for what you can do with it, while an analytic definition is an implementation. And the importance of synthetic methods from this perspective is just an instance of the well-trodden principle in computer science that working via interfaces rather than directly on implementations is the key to proper abstraction, modularity, and conceptual clarity. So then the question becomes, how can we describe and work with such interfaces in practice? And can automation, like interactive theorem proving and stuff like that, help us make sure we're working with them correctly if we have like more exotic axioms that we're not used to working with? And yes?
I was trying to think when I first heard the word synthetic, and it was applied to projective geometry.
Yes.
Because homogeneous coordinates were very popular since you could deal with it computationally with points at infinity.
Yes.
But then the synthetic approach meant that points at infinity and finite points were all the same.
Yep.
And you had a nice axiomatization of that.
Yep.
And so books on projective geometry became very popular.
Yes.
That was the first time I think I heard the adjective synthetic.
Yep. Yeah. Exactly. So this topic of how can we actually like work with synthetic interfaces to mathematical concepts in practice naturally prompts a discussion of logical frameworks. So what is a logical framework? So we already had an NLab quote. Now I have a Wikipedia quote. In logic, a logical framework provides a means to define or present a logic as a signature in a higher order type theory in such a way that provability of a formula in the original logic reduces to a type inhabitation problem in the framework type theory. So that's a lot of jargon. Let's unpack what it means. And so first I'm going to commit a bit of a cardinal sin for people who actually specialize in logical frameworks, so sorry. But I'm going to say that this idea of a signature here, you can basically just think of as a type. If you've ever done any sort of like functional programming, or especially dependently typed functional programming, then we are basically just going to be encoding logics as types in this idea. And so, and the idea here is that, so we have some signature, which again is a type corresponding to some logical theory T here. And we encode it in such a way that the formulae we can express in this Blackboard bold T correspond to types that depend on this type T that we're treating as our sort of signature, such that the proofs of those formulae correspond precisely to terms of those types in the logical framework. So it basically reduces the problem of proving some statement in whatever sort of like logical language you can dream up to just a type inhabitation problem, which is going to be something like dependently typed programming, basically. Yes?
So I should be thinking bold T is like the theory of Euclidean geometry.
Exactly.
For you.
Yes, exactly. Yes.
Can you give a specific example?
I'm going to have some in a little bit, but it's also, so like basically like what Kevin just mentioned is like you could have a sort of signature T that encodes the theory of Euclidean geometry by saying like, okay, there's a type of points and there's a type of line segments that depends on like 2 points you give it and stuff like that, and then some axioms, those follow, and then whenever you sort of add all that structure to your context, then you're sort of implicitly working inside Euclidean geometry now. And that's just what I was about to say. So in other words, we can simulate the logical theory T in a logical framework by encoding it as a type T and then working in the context extended by an element of this type T. So we assume, so going back to this Euclidean geometry example, we assume that there's some type of points and some type of line segments that depends on that, and then some axioms they satisfy, and then we can do stuff with all that structure that we just assumed.
I think the answer is it's fairly obvious.
Mm-hmm.
Something like this is actually not confusing. But you say Euclidean geometry, you think of that as a type, and there are also types of line segments.
Yeah, yeah.
That's why you have
It
a
is.
higher order type theory.
That's why it's higher order. Yeah, because we are actually heavily taking advantage of the fact that you can have types of types and types and types of types, so on and so on. That like most of what we're going to end up doing is like usually at most like second or third order anyway, but it's like still in principle you can go as far as you want.
Wait, is this higher order in the sense of dependency or in the sense of like sub-type, like topos?
It is in the sense of a topos, like as in yeah. So. And note that when we're thinking about things this way, the desiderata for a logical framework, oh shit, I'm mixing up my variables there. Anyway, but desiderata for a logical framework are not generally the same as we would have for a particular mathematical foundation. Because we usually want our foundations, like set theory or et cetera, to be maximally specific within reason about the objects they codify. Perhaps not complete, because per Gödel's incompleteness theorems, that's not possible. But usually we want to assume as many specific properties about, for instance, sets, as we can agree on, and that tends to be contentious, in order to be able to derive as many of their consequences as possible in set theory and mathematics based on it. By contrast, if we're working in a logical framework, then we want to actually be maximally general as opposed to maximally specific. Because we want this logical framework to be capable of accommodating all the foundational logics we might want to work with or encode in it. And so the point then is not to assume any axioms particular to a specific foundation, but rather to find the structure that allows these axioms to be expressed in a common language. And so this prompts one of the main points of discussion here, which is using Agda as a logical framework. And so one claim I'm going to make here is that the Agda programming language / proof assistant has some features that make it particularly well suited to being used as a logical framework. So first of all, Agda is based on Martin-Luft type theory, which is a form of dependent type theory, but in particular has a very nice general semantics. It has a semantics in a wide range of categorical models, in particular all toposes. For instance, the category of sets, and also something that's going to come up a bit later, the category of simplicial sets. And as you'll see in the footnote there, there's some caveats about, because there's different flavors of Martin-Luft type theory, and there's different flavors of topoi, and they all match up with each other in slightly different ways. But so I'm just sweeping that under the rug right now, and continuing on. So, and there's also, yes?
So just on your first point there,
Mhm.
your point is that, in your desiderata for a logical framework, you're saying that you want this maximal generality.
Yes.
That was your main sort of
Yes.
point. And so you're saying because it's based on Martin-Luft type theory, it's maximally general.
Within reason of like, you want to do stuff with like dependent type theory and locally Cartesian closed categories and stuff like that.
How do you navigate that question of within reason? Like, what is?
I mean, it's basically a term of, it's basically somewhat of an art, but yeah. So, and Agda also has a streamlined interface for interactively building proof terms. So, and I can actually, for instance, show that. So let me go over here and pull up my, one of my first Agda files here. And so this is actually some of the like formalization work that I've been doing while I've been here. And this is just like the basic stuff where I'm just building up kind of basic type structure and basic definitions. And so, for instance, you can see stuff here like I've got something for the unit type, which is just a type with a single constructor that's unique. And then also these dependent pair types and a kind of convenient syntax for them. So those are, if you're not familiar, types of pairs where the type of the second element can depend on what the first element is. And then I've got binary product types defined as sort of the trivial case of dependent pair types, where the type of the second element actually doesn't depend on the first. And then we've got basic operations like function composition that we can define using this. And this is actually dependent function composition. So we actually have a type A, a type B that depends on A, and a type C that depends on A and B. And then if we have some function that takes in an x of type A and a y of type B of x and gives us a C of x and y, and a function from x of A to B of x, then we can get a function from x to C of x and f of x, and define it in this way. But just to show how the kind of interactive theorem proving here works, I can, if I wanted to define this manually, again, I could plop this in here and say g circ2f equals this. And then I get a goal here for the type that I'm supposed to be trying to inhabit here now. And I can have Agda refine that goal because it knows it's a function type, so it's going to be a lambda, a function abstraction. And so, and then I know basically what I want to do here. I want to apply g, f and then g, or g and then f, depending whether you're doing it diagrammatically or in function order. So I'll start with g. Yeah, whoops. And then it gives me a goal for what I should apply that to, which should be something of type b of x. And I know I have f, which gives me something of type b of x, if I can give it something of type x of type a. And oh yeah, I just have one of those lying around. And then I'm done.
Could it not have found that x for you?
When you say it's giving me, who's giving you? You say it's giving you.
This.
What are you running?
I'm running the Agda type checker, and it's like interactive mode. And yes, it can also, to answer your question, it can also find, so probably if I delete this, and I just say, find it for me, yeah, it does it. So.
It's almost as good as Copilot.
Yes. Let's see. And OK, so back to, yes?
I'm wondering if you can give me a sense of how you would encode like your geometry example in Agda?
We're going to get to that.
Great.
Yes. Yeah. So, and then here's a big one. So user-definable rewrite rules. So a fairly unique feature of Agda is that you can actually define custom rewriting rules that are automatically applied during type checking. And so to illustrate that, I have another example here where I'm going to talk about how you can actually use that to prove function extensionality. And so, yes?
I know I'm sitting right at the back, but I'm having a little trouble reading this, so it would be slightly helpful if you can zoom in a quick.
Yep.
Yeah, thanks.
Yeah. OK. And so, so Agda is, as previously mentioned, based on Martin-Luff type theory, and actually intentional Martin-Luff type theory. You don't really need to know what that means if you don't already. But one famous thing about intentional Martin-Luff type theory is that it doesn't automatically satisfy function extensionality, which is a real drag if you're trying to formalize mathematical stuff, because function extensionality is just everywhere. But because Agda has support for some of these advanced features like rewrite rules, this is not actually too hard to get around, because we can just add some structure to Agda using these rewrite rules that actually forces function extensionality to hold. And this borrows some ideas from some of the work that's gone on in cubical type theory. So the idea is that we have, so here you'll see I've got some postulates where I'm just adding some structure to the ambient type system in Agda. And so I'm postulating that there's this interval type, I, which has 2 points, I0 and I1. And we're going to, what we're going to do is we're going to encode proofs of identity in elements of types as functions out of this interval. So if we want to say A is equal to B, we give some function out of the interval that maps I0 to A and maps I1 to B. And so the way we do that here is, so now we've got this type IDP, standing for identity path, which takes some type A, which might depend on I, and then has some element A and elements A and B at both the endpoints of that. And then we've got this lambda abstraction for those paths, which says if you give me a function out of the interval into this type A, then I'll give you a path between what that function maps I0 to and what it maps I1 to. And then you can also apply something to the one of these paths to an element of the interval. And then we have this beta law, which, and see, and note here, I am using Agda's rewrite feature to actually promote that to a rewrite rule that will be applied during type checking. And it says if you apply a function abstraction of one of these types to some element of the interval, you just get back the application of that function to that element of the interval. And then we also have these additional rewrite rules that enforce that if you apply a path to one of these endpoints, I0 or I1, you do get back the corresponding elements, A or B, that were encoded in the actual type of that path. And then we also have this Ada law, which says that if you function abstract over just applying a path, that's just the same as the original path you started with. And then I have this notation of this equal sign with a dot over it for paths here. So that just says if you want A equals B, then you have That's a dot equals b is just a shorthand for these paths. And then there's this reflexivity path, which says for all elements a of a type A, you have a is equal to a. And then we can, using that, we can prove function extensionality. So let's see how we do that. So if I open this up here, now I get a goal. So I'm assuming I have two functions f and g from x of a to b of x. And I'm assuming I have this map here that maps elements x of type A to proofs that f of x is equal to g of x. So now how am I going to get a proof that f is equal to g? Well, so remember, and I can actually even say, if I want to normalize the goal type, I'm trying to produce one of these paths. So I'm probably going to want to apply one of these lambda abstractions. And then I'm going to get my refined function here. And then, just going off some intuition here, I'm going to want to apply something to I. And then, so all I have left to do is produce a path with the right boundaries. And I have this digamma that I assumed lying around. And I need something of type x, A, which is this x that I have. And then, voila, I have my proof of function extensionality. Yeah.
Yeah, ask a different kind of question.
Yes.
The Birmingham group, whom I like to follow in their discussions, often in the Martin-Lurf type theory, bring up questions of size and speak about 0 groupoids, 1 groupoids, 2 groupoids, of that. So, for example, it might turn out that the function extensionality depends upon when you say two things are equal over a certain range. It might be a range that you put some size thing on. Do you use that yourself? Do you use that question about different kinds of sizes?
That doesn't really come up in this approach to function extensionality. You can add that and talk about that stuff. But so when you're doing this approach, it's not required that you need to think about that basically.
But for those who know about it, it fits in.
It does. Yes. Okay. Yes.
So, just to basically say what we're going to decide, there's this base Martin-Lurf type theory. It doesn't have function extensionality. Sometimes you might want to be like, well, these two functions are degree of order arguments, and therefore they're the same function.
Yes.
And so now you have this thing where you can rewrite rules so you can prove add function extensionality.
Yes.
Why can you not? What's the difference between that and just adding function extensionality directly?
That's a good question. So you can also just assume function extensionality as an axiom, but then that axiom is now just like a primitive in your type theory. So if you use it in a proof, and then you try to normalize that proof term, like if you construct some natural number based on that proof, it might get stuck on that because it doesn't know how to evaluate it. Whereas these rewrite rules, if you know what you're doing, you can add them in a way that actually preserves this canonicity property of the underlying Martin-Lurf type theory. That, for instance, if you have a natural number you define, it will actually compute to a numeral, which also makes the type checking and the interactive theorem proving generally nicer because then you get better goals because it can actually evaluate them to something you usually understand, although that's also somewhat of a art and science these days, is getting good goals. But so, okay, so so we've talked about sort of, oh yes?
What's the advantage of implementing equality in the way you did as opposed to just using cubicles, Agda cubicles?
I mean, that's a good question. So basically, cubicle type theory is great. I'm not knocking it. It's just for this purpose, for the purpose of the bit of the sort of A, what I want to show in this talk, and B is just sort of the formalization that I'm doing. It's kind of overkill, basically, because there's lots of additional features for a cubicle to support things like higher inductive types and other stuff that you get in HOT, and I don't really need those, and they do complicate things a bit because you get into lots of stuff about like transports and H-comps and all that kind of stuff, and I didn't really want to think about that this time around. But yeah, so okay, so we good to move on? Okay, cool. So now I want to talk about, now that we have this sort of like baseline logical framework, let's talk about doing algebra in it. So one of our questions from earlier, what is algebra? And here's a quote from Michael Atiyah. Algebra is the offer made by the devil to the mathematician. The devil says, I will give you this powerful machine. It will answer any question you like. All you need to do is give me your soul. Give up geometry, and you will have this marvelous machine. And I know I used this quote in my talk last year, but I'm going to use it again because it's a great quote. So, but anyway, I'm actually going to, toward the end of the talk, show how maybe this is like being a bit unfair, because I am going to show how we can kind of like have a nice marriage of geometry and algebra, which I mean, come on, there's a whole subject called algebraic geometry, but like, and what I'm going to get to is not that, but like it's, there's a nice interplay going on there. But so anyway, so here's something I think is a decent answer for what is algebra, which comes from, no surprise, from Bill Lavier himself. So an algebraic theory is a category with usually finite products whose objects are of the form brackets n for some natural number n, such that each brackets n is the n-ary product of just brackets 1. So you can think of it as like it's a category whose objects are kind of freely generated under products from just one object. And the idea is that this object 1 represents the carrier set of the algebraic structure. So like if that's a monoid or a group, that's the set that the group is defined on, or the monoid structure. And the morphisms, f from n to 1, represent the n-ary operations on that set. And then the equations these morphisms satisfy encode the equations of the algebraic structure. And then we say that a model of an algebraic theory T is just a product-preserving functor from T to set. So it realizes, first of all, that one object as some set, and then all of the other n brackets n objects as just products of the that object, and the morphisms as functions of the appropriate arities that satisfy the appropriate equations. And then a homomorphism between models m and n of some theory T is just a natural transformation of those functors. And so examples of algebraic theories you can encode in this way are all the usual ones, monoids, groups, rings, etc. But there's some interesting non-examples, because actually one upshot of this way of describing algebraic theories is it actually lets you say what isn't an algebraic theory. And so some non-examples are categories. Categories are not an algebraic theory. They are an essentially algebraic theory, but if you don't know the difference between those, don't worry about it. And also very famously topological spaces, which kind of makes a bit more sense because like topological spaces are some sort of geometric thing, not an algebraic thing, and so on. But we're gonna end up playing around with that a bit and finding some interesting ways to talk about some of these sorts of things in an algebraic way toward the end of the talk.
Models of Euclidean geometry, also a non-example.
Yes. Yes.
What I mean by it's like categorical. So
Yeah. Okay, and so how are we going to get these sorts of algebraic theories into Agda? And so the idea here, before I show you the actual Agda code, is rather than assuming operations of all finite arities, we're instead going to have a parametric notion of algebraic theories over a family of types B, dependent on some type A, and those represent the available arities. So the type A is sort of like the type of arities, and this B type family sort of like decodes each arity to the type that actually is that arity. And these arities can be finite or not. There's no restriction on it. And so given this structure, an algebraic theory is going to specify a type op of operations. So each element of that type we think of as an operation on the algebraic theory. And then for each operation, we have an element of this arity type A, arity of O, specifying the arity of the operation O. And then we have a type eq of equations. So each element of that is going to represent an equation that we have in the theory. And then for each equation, we have an arity of the free variables occurring in that equation. And if this is looking a little opaque to you, don't worry, I'm going to get to an example right after this. And then for each equation, E in eq, we have elements left-hand side and right-hand side, which are going to be trees built out of the operations we had on the in the algebraic theory. So if you're more syntactically minded, you can think of those as syntax trees. And importantly, the leaves of those trees are going to be the variables that we specified with the arity of the equations. And then a model, M, of a theory T, specified in this way, is given by a carrier type x of m. And for each operation in the theory, a function from x to the power of that arity back to x itself, such that when you evaluate those syntax trees we had in the equations using these operations, the encoded equality actually holds. And finally, a homomorphism between models m and n of a theory T is given by a function from x sub m to x sub n, such that for each operation, the following square commutes. And so an example of how we can use this to encode sorts of algebraic structures is the theory of monoids, and I can show you that in Agda. So, Lavier. So, first of all, I've got my definitions here of an algebraic theory, which is encoded in this type Lavier. And then I've got this type of models of a given algebraic theory, which is just as we specified, and also homomorphisms, model hom, between those. And so now if I go down, okay, so now I have the theory of a monoid. So first of all, I'm going to encode the types that are going to stand for the actual arities. I need to specify that. And we don't actually need to assume arities of like all natural numbers, because if you think about like the operations and equations you have in the theory of a monoid, well, you have like a zero array operation that gives you the unit element, and you have a binary operation that gives you the monad multiplication, and then you also have a unary equations for the left and right unit laws, because those both have one free variable in them. And you also have ternary equations because for associativity, because that has 3 free variables. I've got types here for 0, 1, 2, and 3, and also a type 4, which I'm going to actually use to represent the type of all finite types less than 4, basically. And that's going to encode my arities, which I have here. So if you have 4, 0 maps to 0, 4, 1 maps to 1, 4, 2 maps to 2, 4, 3 maps to 3. And then I've got this type of monoid operations. Yes?
So we did that to avoid just having some, why not have in your notion, so every specific algebraic theory has its own notion of arity.
Yes.
Well, what's the advantage of that? Well,
You will see when we get to the next part of the thing. But it mainly gives us a lot more generality, because like so in this case it's making it simpler, so we don't have to like keep doing a bunch of long arguments by induction when we're talking about different arities if they were defined as natural numbers. And then in later examples it's actually going to be interesting, because then we can have arities that aren't just like the normal finite types you would think of.
If you did give it, I missed a notion of morphism between algebraic theory. Is that defined?
You can define it. I don't have it defined in here yet. So, yeah.
Does this individual notion of arity cause any complications, or is it just
No.
you do the obvious thing?
You do the obvious thing. Yeah. I've got a type here for the monoid operations, the m0 and m plus, and a type for the equations, the left identity, right identity, and associativity, and and then I have this algebraic theory of a monoid. And so I say that the type of operations is just that type of operations I just encoded, and the arity of each operation, so the 0 element has arity 0, and the monoid addition has arity 2, and the arity of the left identity and the right identity are both 1, and the arity of the associativity, the number of free variables in it, is 3. And then to actually encode these left and right identity equations, we have these syntax trees. And these might look a little scary, but if you sort of like think of them, so this says that if I have plus here applied to this function that takes in some element of the type 2, so it's going to be some pair of things, and so it maps the 0, the 2, 0 to this, the 0 element of the monoid, and it maps the 2, 1 to a leaf, which, and remember, the leaves represent the free variables in these equations. And then we're saying the right-hand side of that is just a leaf, which is just a free variable. So this is saying that if you have 0 plus x, that equals x. And we're encoding that as basically a tree that's like 0, x plus equals just this x. And then similarly for the right identity, and then associativity gets a little more hairy just because it has more applications, but it's the same idea. And then so let's look at an example of what we can do with this. So let's define the OR operation on the type 2, which is basically, you can think of as the Booleans. And so it says that if you take 2, 0 and OR that with x, that just gives you back x. And if you have 2, 1 and you OR that with x, that gives you 2, 1. And so now let's prove and then we prove the left and right identity, which you can actually just prove with reflexivity and pattern matching on this, and likewise associativity. And then you can just encode the monoid structure there exactly as you would expect. So the carrier of it is this type 2. The 0 element of that is 2, 0. The plus operation is 2 OR. And then the proofs of the equations that we had for that are just those left and right identity and associativity things we just proved. So to show this interactively, let's do another example, and also for how this works for homomorphisms. So now let's do and. So I've defined and here. So and is the dual of or. So we have 2 and of 0 and x is just 2, 0, and 2 and of 1 and 2, 1 and x is just x. So how are we going to prove the left identity? Well, I think that was just part of our definition, so that should just follow by reflexivity, right? And surely it does. How are we going to prove the right identity? Well, that one wasn't part of our definition, so we probably need to do some sort of case analysis. So how about I case on x? And Agda just does that for me. And then once I case on x, hopefully both of those just follow by reflexivity. And of course they do. And likewise for associativity, if I'm somewhat smart about this, I can think, aha, if I just case on, okay, load buddy. If I just case on x, then I can also reduce these to things that follow by reflexivity. Okay, and then build the same monoid structure for this AND operation. And then finally, to show how you prove something as a homomorphism in this, let's prove that negation is a homomorphism from the OR structure on 2 to the AND structure on 2 by De Morgan's laws. So we have this negation operation from 2 to 2, and it just takes 2, 0 to 2, 1, and 2, 1 to 2, 0. And so now I have here a statement of De Morgan's laws, which says if I have 2 and of the negation of x and the negation of y, that's the same as the negation of 2 or of x and y. And then let me, I think I can do this by pattern matching again. Yep. Riffle. Because my Agda Agda mode for VS Code is slightly broken, and I haven't fixed it yet, so I'm just being careful. So okay, and then from these we can straightforwardly prove that negation is indeed a monoid homomorphism by just filling in this type of model homomorphisms that says that the underlying function of that homomorphism is this negation operation, and then we have just the fact that it preserves the 0 element by reflexivity because that was part of the definition, and then the proof that it preserves the plus operation is just De Morgan's law. And okay, so that's all great.
Do you see what your time is?
Yes, I do. I will be done right about on time. But so yes. Oh, okay, cool. Yes. So okay, let's go slightly fast here. So algebraic theories have some key properties. First of all, there's this monadicity property, which says that, like, for each algebraic theory, you get a monad, and the models of that algebraic theory are precisely the algebras of that monad. And there's also this duality property, which says that the actual category that we defined this algebraic theory over in the Lavier style thing is actually just equivalent to the full subcategory of finitely generated, the opposite of the full subcategory of finitely generated free models of that theory. And proofs of these in Agda are currently work in progress. But so this prompts the question, why bother proving these things if they're already known results in Agda? And the answer to this is that it's precisely that generality of Agda as a logical framework that lets us take advantage of this to get some genuinely novel results. Because we prove things in this more austere setting, we can use this framework of algebraic theories to talk about things that on the face of it aren't algebraic, like categories. So toward categorical algebra, wouldn't it be wonderful if we could encode categorical structures like limits, colimits, monoidal structures, et cetera, with the same ease and simplicity that we just encoded the theory of a monoid and prove some stuff about it. And actually we can if we use a synthetic approach. And so what we do is we extend the language of Agda using postulates and rewrite rules to model certain aspects of the internal language of the topos of simplicial sets, which contains in particular cat as a full subcategory. And so here's how we do that. So quick recap. For each n natural number n, the standard n simplex is the category freely generated by a string of n composable arrows, like so. And then the simplex category is just the full subcategory of cat spanned by these standard simplices. And then a simplicial set is a functor from delta opt set, i.e. a presheaf on delta. And given a simplicial set x, we say that the elements of the set x of n are called the n simplices of x. And so this determines a functor n from cat to set called the nerve that maps the category C to the simplicial set n of C, whose n simplices are the functors delta n to C. And here's a fact. The nerve functor is fully faithful and has a left adjoint, exhibiting cat as a reflective subcategory of the simplicial set of the category of simplicial sets, if you know what that means. And so what this basically means is that simplicial sets is actually kind of a nice place to do category theory internally, especially because it's a topos and it has an internal language corresponding to a form of Martin-Luft type theory. And so the question is, what axioms do we need to add to Martin-Luft type theory or Agda to capture the relevant properties of this language? And there's a lot of ongoing research about this, but the only thing I actually really need is that simplicial sets is the classifying topos of the theory of bounded linear orders. And so I'm going to skip over a bit what that means. You can ask me about it afterward. But so the idea here is that the internal language of simplicial sets comes with this internal bounded linear order, so linear order with a top and a bottom element. And we can use this to encode a bunch of geometric or categorical structure. So we have just this abstract type of the one simplex, which is just a line segment that goes from delta 0 to delta 1. And then we can use that to build up more complicated things like a two simplex, a triangle, which is just the subtype of the Cartesian product of delta 1 with itself, consisting of pairs x, y such that x is less than or equal to y. And then we can also talk about the inner horn, which is sort of the upper boundary of the two simplex. And then we can talk about types satisfying the Siegel condition, which says that every map from this inner horn to A factors uniquely through the embedding of that inner horn into the two simplex. And here's a fact. A simplicial set X is the nerve of a category if and only if it satisfies the Siegel condition in the internal language of simplicial sets. So this is how we can talk about categories internally to the language of simplicial set. And now here's a very cool thing. The Siegel condition is algebraic in the internal language of simplicial sets. So we can actually build a algebraic theory internally in simplicial sets that encodes the Siegel condition. And what it just says is that basically for each map out of this inner horn into the carrier X, we get a map from the two simplex to X, which has the corresponding boundary, and we enforce that with equations, and also an equation saying that that filling is unique. And that gives an algebraic theory for Siegel objects or categories. And then we can go further with that and talk about more complicated categorical structures, like a terminal object. And so I'll skip over the details because I see I'm running out of time here. But basically, that's all still algebraic. And we can go even further and generalize this definition of a terminal object to something that lets us talk about arbitrary limits by basically talking about when we can have a sort of like, for each diagram of some shape in a type, we get the type of fillings of that diagram isn't necessarily unique, but it has a terminal element. And so we can build a theory like that. And that, for instance, lets us get the theory of a type with all pullbacks as the version of this where the diagrams and the filled diagrams are basically this cospan diagram where you have two things mapping into a thing, and then the commutative square diagram as sort of the filling of that, because a pullback is just a terminal commutative square that completes some given cosband. And so, conclusion, remaining work on this project is to finish the proofs of monadicity and duality for algebraic theories in Agda, and then prove meta-theorems externalizing the results obtained in the internal language of simplicial set. In particular, I have this conjecture that the simplicial Lauvier theories, i.e. algebraic theories internal to simplicial set, externalize to some sort of double theories in the manner of Lambert and Patterson. But with a twist, they're not just double theories with products, they're double theories with products and tabulators. And then blah, blah, blah. And then I also foresee applications of this to syntax and semantics of type theory. If you're curious about this, ask me about it. And then the just moral of the story I want to drive home is that when you're seeking to make precise a mathematical concept, ask first not what it is, but where it lives, because that might tell you a lot about how you can build a nice synthetic framework for doing stuff with it elegantly. And so, yeah, thank you.